Good afternoon, everyone. My name is Mohammed Abdurazak Halim, and my co-authors are Ishraq bin Shafiq, Fazle Rabbi, and Dr. MD Khalil Rahman Sir. And I'm going to be talking about our conference paper titled Exploring the Opportunities of a Balloon Satellite in Bangladesh for Weather Data Collection and Vegetative Analysis. Satellites have proven to be very useful to our civilization. Using a satellite, we can collect various data from space regarding our planet and use them in various purposes. We can use these data for weather pattern, we can use this data for space research, we can even use the satellite itself for telecommunication. Now, having that said, these satellites are quite expensive and have a very high development cost, even the small ones, that is the CubeSats or the nanosatellites. The table here displays the development cost of a few satellites. The table is the courtesy of Delft University of Technology. Now, having that said, BalloonSat is simply the assembly of various sensors, various circuits or modules assembled together and sent to high altitudes using a balloon, hence the name balloon satellite. What we did was use off-the-shelf components to create our own balloon satellite circuit, send it to high altitudes using a balloon, and collect data and transmit it back to the ground station and analyze them. The circuit components that we used, off-the-shelf components, that is Raspberry Pi module, Raspberry Pi camera, Adafruit UV sensor, Adafruit IMU module, Adafruit GPS module, and XB modules from Digi International. The circuit setup is as shown in the circuit diagram here. All the components are paired up with the Raspberry Pi, and the Raspberry Pi is powered by a battery. The onboard process is quite simple. After the circuit has been turned on, all the components take a delay of 2 minutes. After a 2 minutes delay, they start collecting data and send them to the Raspberry Pi. The Raspberry Pi then processes all these data into one string and sends them wirelessly via the XB module to the ground station. Now, on the ground station, which is simply another XB module and a laptop, all these string data are collected, saved, and then parsed and delimited in order to obtain each individual data separately. These data are then displayed in a GUI and saved in an Excel file. Now, the GUI we made, it was made in LabVIEW, has 6 tabs, 6 separate tabs. The first tab shows the connection tab. Here we can see whether the connection was established or not, at what baud rate is the connection established. Also, we can see the raw data. The following tab is the GPS tab. Here we can see the date, the time, the latitude, longitude, in simply the GPS information. We also have a plot option which brings up a new window which will display a map and the path that was traveled by our balloon satellite. This map was coded in .NET. The following tab is the gyro tab. Here all 3 gyro axis data are going to be displayed in a graph. The next tab is the IMU tab, or you can say the navigation tab, that is. This tab displays the pitch, the heading, the roll, and also the altitude of the balloon satellite. The light sensor tab displays the visible light, IR, UV index, mainly the UV sensor data. And the last tab displays the weather data, that is barometric pressure, atmospheric temperature, the altitude in a graphical manner, and the core temperature, the internal temperature of our circuitry, the CPU temperature, that is. This is an image of our circuitry assembled in the PCB board, and this is an image of our ground station. As you can see, the ground station is simply an XB module connected to a laptop, which means many XB modules can connect to our balloon sat. There is no restriction, and also at the same time restrictions can be also implemented. This plot shows the temperature plot versus time. This temperature plot, this data was collected using our balloon sat over a period of 10 hours. Now, as I've mentioned earlier, all these data that are being collected and displayed are saved in an Excel file on the ground station. This is a sample of our Excel file, which contains all the saved data. As you can see, all the data are saved in a proper manner. Now, as I've mentioned earlier, one of the components, off-the-shelf components, was a Raspberry Pi camera. The reason for the Raspberry Pi camera was to approach vegetative analysis. Color thresholding is simply a process by which we replace certain pixels of our image with 0 and other pixels with 1. These certain pixels which will be replaced by 0, will be determined by a constant, a predetermined value of our own, or a preset value of our own. If the pixel of that image falls below this constant, the pixel will be replaced by 0. If it is greater than the constant, it will be replaced by 1. You can see an image taken by our balloon set has been thresholded in order to find its thresholded image. In other words, separating each color. This thresholding process was performed using MATLAB. MATLAB has a thresholding app which helped us perform this thresholding. Now the image that we have showed earlier, we use that image in order to find its RGB ranges. This is here we can see the maximum value and the minimum value of the RGB. This is our original image, and this is our thresholded image. You can see all the pixels containing the value within our constant are white, and those that are not, they do not contain value within our range, are black. We used a boundary detection algorithm in order to draw boundaries around regions that contain pixels or RGB colors within our desired range. The overall process: here is our original image taken by our balloon set, and here is the processed image. You can see all those green regions have been covered by a boundary or circled by boundaries. The process is not 100% accurate, but it has identified those regions. By this process, we have determined that the image has 48.4% green pixels. Now, as I've stated earlier, the main reason for this camera was in order to do vegetative analysis. Now, in South Asian countries, the most common vegetation is crops. Now, our farmers require nitrogen fertilizers in order to increase the yield of crops. And in order to measure these nitrogen concentrations within the plants, they require a leaf color chart, which was developed by International Rice Research Institute. This leaf color chart contains 4 strips of green shades, and each strip determines different levels of nitrogen concentration. This table here displays the nitrogen concentration level for each strip. As you can see, the second strip displays the critically low level of nitrogen, and the fifth strip displays the surplus of nitrogen concentration. What we did with this leaf color chart is we digitalized it. We took this leaf color chart, took each strip separately, found its RGB composition, and took it as a constant. We used these constant values in MATLAB in order to judge all the other images. The images that are taken by the balloon set are retrieved after the flight of the balloon set is complete. Those images are taken, and then using MATLAB and these constant values, we find which regions of our field falls within which strip, and using that we understand which regions have a surplus of nitrogen, which regions have deficiency of nitrogen, and which regions have the perfect amount of nitrogen fertilizers. Now, what was the problem with the traditional leaf color chart itself? Well, it was a long process. If the farmers had huge farms, they had to grind through the entire field, which would take a long time. And also, the system they use is they go to particular points of the field and take a particular crop plant and match its leaf color with the strip, which is not really accurate because not every plant is getting the equal dosage. Its neighboring plants may not have the exact nitrogen concentration it has. So by digitalizing it, we can increase its efficiency and make the process faster and simpler and effective. So in conclusion, we accomplished making a cheap balloon satellite, that approximately cost us like around $400. We successfully transmitted data from high altitudes and received it in the ground station and displayed it, as well as saved those data for analysis. We successfully were able to do boundary detections of certain defined constants. In other words, we can use this algorithm in order to find regions of vegetation. We were also able to digitalize the leaf color chart process, the nitrogen concentration identification process. We also developed a GUI of our own in order to in order to display all the information that is being transmitted from our balloon set. And at the end of this, we can understand that using a balloon set, space research can be achieved in developing countries at a very cheap rate. Thank you everyone for your patience and your time. These are our references.